We've looked at problems that involve finding areas under normal distributions, and those areas correspond to percentages. Those problems entail us taking a certain data value and finding its z-score, and then finding, the percentage of data that relates to that z-score in a particular way. What we're going to do here is sort of work in the reverse. So, as I wrote here, it says we learned to use z-scores to find areas and percentages and percentiles under the normal curve. But what if I gave you the percentile and asked you to find the z-score, or even the score in context that goes with that percentile? So if I said what z-score represents the first quartile in the normal model, what I'm basically asking is what z-score represents the 25th percentile. That's what the first quartile means. So in other words, what z-score represents the 25th percentile. Okay, or you could say what z-score cuts off the bottom 25% of the distribution. I guess you could also say what z-score cuts off the top 75% of the distribution. So the way this works is a function on the calculator called inverse norm. Okay, and so we'll get some practice using that. The first thing to point out is if you look at the button diagram I have here, there's only one input. So with the normal distribution, you'd have a couple inputs, right? You'd have to input, your first z-score, or 100 or negative 100 if you were going off to a tail, and then the other z-score. The input for inverse norm is just one number, which is the percentile you're interested in. So I'm just going to indicate you input percentile, and then calculator will output the z-score corresponding to that percentile. Okay, so we're going to do an example in a second. Notice that it's a left, sort of a left bias button, meaning that you have to punch in the area, the percentage that goes with the area to the left of the z-score you're interested in. So like if I asked what's the z-score that cuts off the top 75th percentile or percent, you can't put in inverse norm 0.75. Okay, that's not going to give it to you. You have to translate that into the button that you would push to get the top 75%, which happens to be cutting off the bottom 25%. So this will be more clear when we do an example, but just to kind of preemptively clear up that confusion, I figured I'd mention it here. So this problem says, suppose the weights of a breed of dogs are normally distributed with a mean of 17.5 pounds and a standard deviation of 3 pounds. And then it says, what weight would a dog of this breed have to be in the top 8% of weights? So again, we're asked for the weight of a dog that is in the top 8% of weights. And to answer this question, what we first have to do is we have to find the z-score that goes with the top 8% of weights. So in our diagram, we should note that the top 8% would be somewhat like here. It doesn't have to be perfect, but let's just say that's 8%. So if that's 8%, okay, we're interested in that z-score. Okay, now that z-score, in order to get it, this is where you have to be a little careful. So I kind of started with the harder problem. In order to get that z-score, we need to punch into the calculator the inverse norm of that percent, which is 92%. Okay, the calculator won't understand the direction. It won't understand we want the top 8% unless we punch in inverse norm 0.92. So the z-score that goes with that percentile on our calculator we're going to punch in this button. Okay, again, that's just because the calculator is programmed that way. So I hit second variables, go down to number 3, put in 0.92, and I get 1.41. Okay, so that's the z-score that goes with this. Now the problem is that that's just a z-score, right? That doesn't tell me what the actual the weight the dog has to be. So we've got to convert the z-score into the actual weight of the dog. And to do that, we use our little formula for finding z-score. So we know that the z-score is our data value minus the mean. Let me use the population mean symbol divided by the standard deviation. Now I guess I really should define the variable x, what it means. So we're going to say that x represents the weight of a dog. Okay. So this is where you have to note that we know this because we just found it, right? The z-score that goes with the top 8% is 1.41. We know that the standard deviation is 3 pounds. That goes there. We know that the mean for this population of dogs, 17.5. What we don't know in this case is the actual weight of the dog, or dogs, that cut off that top 8%. So there's a little algebra you need to do here. So to undo multiplying by and dividing by 3, we times by 3. Okay. Oops. And so that gives me, and so then I'll just do it all in one shot. Then we're going to add 17.5. Okay, so in general, it's going to be 3 times, and that will get you the actual weight of the dog. So 3 times 1.41 plus 17.5. 21.73. Okay, so what weight would a dog of this breed have to be in the top 8% of weights? The dog would have to be, let me shrink this a little bit. The dog would have to be now you could say, this is what you really want to say. The dog would have to be 21.73 pounds or greater, right? Because as soon as you're 21.73 pounds, you're like right on the line, and anything greater, well, you are in the top 8 percentile, or the top 8%. I keep misusing that word. 21.73 pounds or greater, or heavier. Okay, so there's a little algebra to do. If you're someone who likes formulas, I guess what you could say is that in order to get this, you know, the data value is always going to be the z-score times the standard deviation. So z-score times the standard deviation plus the mean. Okay, all I've really done there is just, sorry, I'm using the wrong symbol again for mean there. See mu. So if you're someone who just really relies on formulas, that's really all we're doing. But if you're savvy with the algebra, it's usually best just to anchor your knowledge to this. Okay, and then just do the algebra. But in any case, we've introduced the inverse norm button. We know that that gives a z-score for a percentile that you're interested in, and then you need to work backwards to take that z-score and convert it into a actual value that corresponds to the context in the problem.